Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today, we're not solving a problem, but I'm going to give you some tips and tricks and really want you to understand the Nusselt number. Nusselt number is extremely important if you're learning heat and mass transfer, so let's jump right into it. What I want to cover with you guys today are these things. We're going to talk about the definition, we're going to understand the number better, we're going to talk about some equations that are useful, talk about its units and its usefulness. Okay, so let's start with the definition here. What we want to do is, let's start by defining it mathematically. So the Nusselt number, NU, is defined 1, 2, 3 as the ratio between the heat due to convection divided by the heat due to conduction. Okay, so it is a ratio between the heat flux, that is watts per meter squared, or watts per unit area, power per unit area, that due to convection, divided by the amount of heat, same thing, power per unit area due to conduction. So note that when we look at this mathematical definition, what the Nusselt number is doing is it's giving you what is the enhancement that you get due to convection. And as a matter of fact, that's what I would love for you guys to write down somewhere and to remember. Remember that the Nusselt number is measuring the enhancement of heat transfer due to convection. Okay, and I always ask my students to write this down and to really embrace this concept as a way to understand the Nusselt number. So that's the definition right here. First thing we wanted to cover in this video. Boom. Okay, so now let's try to understand it a bit better. If you look at this definition here and you see the ratio between the convection and the conduction, really what this is saying is, okay, if I have a situation in which I'm going to have heat transfer happening, and this would happen due to conduction, then by having convection, I'm going to have this enhanced. Why is that? Well, we know if you look at let's say this is a water here, okay, so water inside this cup, and we have a source of heat down below here. So we have a little fire there, purple fire, and we have energy being transferred into the bottom of this flask. Let's say this is, I don't know, steel. This bottom of the flask, because there's a delta T, we're going to have heat transfer going from the steel into the water molecules that are around here. And this is happening, right, as the bottom of the flask is increasing its temperature and it's transferring that energy to the molecules of water there. Once that happens, because the molecules of water are fluid and they can move in this fluid more freely than the molecules of steel can, the atoms inside the lattice of the steel structure can, once this gets hot, it's going to vibrate more, increase its volume. Because it increases its volume, it decreases its density, right? As the volume increases, the density decreases. Therefore, because of the buoyancy forces, it will go up. So this molecule here that's now hotter than the molecules around it is actually going to go up and come up here. And we just observed heat transfer due to convection. So first we had due to conduction from the steel flask into the water molecule. And then we see that same water molecule traveling upwards into a different place. So we're just seeing heat go from this position here into this position here due to convection. So this is an enhancement we get because this molecule can now travel faster. And what if I had, for instance, a little pump here on the corner, and this pump is circulating water like so? Then not only am I going to have that little water molecule going upwards because it wants to go upwards because it has less density, but also we're going to have external forces pushing it and making this same, hotter molecule travel bigger distances, and we're going to have an even greater enhancement of heat transfer. So this is what the Nusselt number is trying to measure. It's how much more heat transfer are we getting because we have convection taking place. Okay, so with that in mind, now that we're into this box of understanding it, let's think about the following. The Nusselt number can be, let's put basically three options here. Nusselt number can be greater than 1, Nusselt number can be 1, and the Nusselt number smaller than 1. Okay, if the Nusselt number is greater than 1, this is telling us what? Well, it's basically telling us how much convection is helping us, right? If you think back to this definition here, how much enhancement are we getting in respect to what we would get if we had only conduction taking place, right? If our Nusselt number is 1 precisely, it basically says, well, we're not getting any enhancement whatsoever, right? If it's 1, then the rate of convection and rate of conduction are the same, and therefore there's no enhancement. So really convection is not helping me here at all. And if the Nusselt number is smaller than 1, it's basically saying that my convection is somehow hindering heat transfer. And this does not happen. Remember that the definition, that's why I always ask you guys to remember this. The definition is that the Nusselt number is the enhancement of heat transfer, right? Not the change in heat transfer. So it's the enhancement precisely. So if that's the case, then this is not possible. And if you get a Nusselt number smaller than 1, it means you made a mistake. Okay, there's something wrong in your numbers, something wrong in the positions of the equations that you're putting. Go back and check, because this cannot happen. All right, so here we have enhancement, all good. Here we have no enhancements. Basically, conduction is taking place as dominant heat transfer mode here, and smaller than 1 is you made a mistake. Don't fall on this trap here. All right, so then that kills the understanding part of this. Next one, let's talk about some of the equations. So basically, the Nusselt number, while the above is its definition, the Nusselt number can also be calculated with the convection coefficient times the characteristic length. I'm just going to put CL here for characteristic length, divided by the conductivity of the medium that we're talking about. Okay, and this is helpful because often what we're trying to find is this guy here, which is a pain to find in real case scenarios. Right, finding that coefficient is very, very hard. And then we're multiplying that by a characteristic length. And the reason why I'm putting it like this is because this is going to be dependent, very important, this is dependent on the geometry of what you are studying, right? So the classic example that we start studying, and you can see there's a video that we start doing it here if you want to check it out. The classic example that we start doing is the flat plate analysis, right? So we have a flat plate, has a certain temperature here, let's call it T1, and then we have T infinity, which is the temperature of the fluid around this plate, so we're going to see heat transfer taking place. In this case, in this specific case of the flat plate, the characteristic length is the length of the plate, right? So where I have the CL here, I would just have L for the plate. If we have a pipe, however, if we have a pipe that's carrying water or something, then the characteristic length is going to be the diameter if we're talking about the delta between the pipe itself, the wall of the pipe, and the fluid inside, right? So then this is not L anymore, this is diameter, and therefore that's why I have that as characteristic length, because then you know not to go with only one dimension that you memorize. This is dependent on the geometry, okay? And then K is going to be the conductivity of the fluid. Next up, units. So if we look at any of the equations we've been talking about so far, it's clear that the units of the Nusselt number are non-existent, right? It's a non-dimensional number, because if you look at what we're doing here, by definition, we're dividing things that have exactly the same unit, namely unit of power over area. So we're taking the heat flux due to convection, dividing that by the heat flux due to conduction, and that, because they're the same unit, we end up with 1. So there's no unit on Nusselt number. But if that's true there, it also needs to be true here, and indeed it is, because if you guys recall, let's do a little unit analysis real quick. If you guys recall, the unit for the convection coefficient is watts per unit of area, unit of temperature. The characteristic length is just a measurement of distance, and then the conductivity is watts per meter per unit of temperature. And therefore what happens is, as you can probably imagine, Kelvin and Kelvin go away, watts and watts go away, and then the meters squared goes away with the meter squared. So we're left with nothing inside our unit analysis, which and then shows that the Nusselt number is a non-dimensional number. All right? So that's the third thing to know, or fourth thing to know about this magical number, is that it doesn't have any units. If you're doing your math and you find a unit at the end of it, you also made a mistake, go back and check what you missed. All right, and then last but not least, what is the usefulness of the Nusselt number? The Nusselt number is actually quite useful. It's used a lot in heat transfer problems, be it theoretical if you're studying, doing this for school, or in practical terms. Why? Because as it turns out, the Nusselt number also has some relationships with things that are much easier to calculate, right? So depending on the situation that you have, you're going to have Nusselt numbers proportional. Let's do proportional to Reynolds to a certain power and Prandtl to a certain power. All right, and this is simplifying a lot, but basically, when you're studying heat and mass transfer, there's a bunch of equations that relate Reynolds and Prandtl to Nusselt. And if Reynolds and Prandtl are easier to calculate, and they are, because basically this is something you can get with the conditions of your problem, the velocity, the density, the viscosity, those good things. Prandtl is also something you can get out of thermodynamics property tables. Then it's much easier to calculate Nusselt. And with Nusselt, you can calculate the convective coefficient, which again is a pain in the ass to be able to find. So the whole reason why Nusselt is important generally is because we're after H, and we can find H using this relationship here, and then we can find Nusselt using the different relationships that are going to pop up depending on your problem. So that's why Nusselt is a useful number. It's because it's a non-dimensional number that we can correlate back to the coefficient. And as you guys know very well, the coefficient is helpful because the way that we calculate convection is by relating the coefficient with the area and the difference in temperature, right? So the whole idea, and this comes over and over and over again when we're studying heat transfer, is if I want to know what is my heat transfer, and there should be a dot here to show this is a rate. If I want to know what my heat transfer is, I need to know what is my convective coefficient. To get my convective coefficient, I generally need to resort to Nusselt. To be able to resort to Nusselt, I generally need to find things like Reynolds and Prandtl and then do the relationship back all the way. Okay, so that's why the Nusselt number is useful. That's the last thing I wanted to talk to you guys about in this video. This is something that we always do in class. I always go over this and explain, but I thought a video here on YouTube would be something useful for people that are not necessarily my direct students. If this video was helpful, please consider leaving a like. If you have any questions about this, just comment down below and I'll try to address them, and we'll talk soon.